I am sure you know this already, but there is a big difference between when substances mix and when substances react. When substances mix, molecules are getting their positions shifted around, but they don't interact with other molecules. On the other hand, a reaction can be characterized by molecules interacting with each other. It is easy to think that it is only a chemical reaction if new compounds are formed, but sometimes, ions are formed of the same element. An easier way to think about it as a chemical reaction involves the rearrangement of electrons. For example, the decomposition of ozone only involves oxygen, but breaks it into a double oxygen molecule and an oxygen ion. Although only oxygen is involved, it is nonetheless a chemical reaction. If substances share electrons with each other when covalent bonds are formed in the formation of larger or different molecules, you can think of it as the rearranging of electrons, and is hence a reaction. A sea of electrons doesn't count because metals naturally exist in that form, so nothing changes, so is not rearranging. You may be wondering which is stronger out of ionic and covalent bonding. This is a complex question. Let's look at different sides. Let's take a single ionic bond and a single covalent bond. A bit of heat is able to separate the ions from each other, a fact that is taken advantage of in electrolysis. A single covalent bond must be broken with either a chemical reaction or enough heat to decompose it, which is a huge amount. Adding to this, ionic compounds can even be separated by simply dissolving them. Take salt for an example, it dissolves in water with little to no problems. Furthermore, an example of a giant covalent structure is a diamond, which is the hardest substance recorded, harder than any metal, which means if we were to compare an ionic and covalent lattice, the covalent one is far stronger. However, ionic lattices are extremely common among ionic compounds, whereas covalent structures are much rarer, which may lead some to conclude that overall ionic is stronger, as lattices lead to very strong bonding. The objective for molecules involved in either ionic bonding or covalent bonding is gaining a full outermost shell, which most often means a full 8 electrons, but in some elements too, as they only have one shell E.G hydrogen. An outermost full shell stabilizes the atom, and would result in the atom being non-reactive among other things. This is known as a stable noble gas structure. If an element already has a full outer shell, it doesn't need to share, take or give electrons, and hence will not react, which is why noble gases are called noble, which is a misleading name since violence is always the answer. Noble gases are the elements at the far right end of the periodic table with full outermost shells naturally and not even-wind ions. Noble gases are all in gaseous form because having a full outermost shell means they naturally exist in single atoms. A simple molecule means there are very few intermolecular bonds which are very weak. Having a full shell means they don't interact with other molecules, so there are little to no intermolecular forces. This means there is very little restriction to atoms moving around, which means they need very little energy to move, so have low boiling points, and most commonly exist as gases. Back to ionic compounds. You can work out the charge on an element's ion based on how many electrons it naturally has, and how many it needs to lose or gain to be complete. Don't forget that when an atom loses or gains electrons, its charge changes because its protons aren't affected, so the relative charge changes. In a sea of electrons, electrons are able to roam pretty freely, although you should make the clear distinction. A sea of electrons happens in pure metals and not ionic compounds, since in ionic compounds, the electrons are taken. It is easy to make this mistake. In an ionic lattice, you have positive and negative ions arranged in such a way that a given ion is surrounded by an oppositely charged ion in every direction, and attraction is exerted in every direction equally, leading to very strong bonding. Finally, onto covalent bonding. You are probably wondering why individual bonds have higher or lower energies, E.GCSE bond having more energy needed to break it than a CC bond. Since one atom in the bond may be larger than the other and contain more protons, the more positive one will pull the shared electrons towards itself, making it slightly negative as a result, while the other is made slightly positive. This furthers the attraction between them. Key word is slightly, as it is nowhere near the amount of charge found in ions. A bond between two of the same element E.G, a hydrogen-hydrogen bond, will not be strong as the pull on the electrons is equal. Bond strengths vary based on the elements involved for the reasons previously listed. You are probably wondering why only ionic compounds and metals can conduct electricity. Remember what electricity really is. It is a flow of charges. So only substances with free charges, such as within a sea of electrons or a liquid-state ionic compound or solution, can conduct. Speaking of seas of electrons, the fact that electrons are free are what allows a metal to be malleable and ductile, allowing it to be shaped into sheets, wires and all sorts of shapes while still being tough. Since giant covalent structures share their electrons, giant covalent structures are harder to find, as there are fewer arrangements which happily work out in all atoms having a full outer shell with no more or no less, and that can be repeated regularly in a large structure. Ionic compounds don't rely on sharing electrons to bond, and instead rely on opposite charges attracting, which makes them more versatile. In an ionic compound, one atom just has to hand over its electrons to another and let attraction do the rest. In covalent, it's not so simple. Time for some more real talk. An atom is determined by its number of protons instead of neutrons or electrons for a number of reasons. Protons add both significant mass and charge to the atom, where neutrons only add mass and electrons only add charge. Although it is the distribution of electrons which makes substances react chemically, electrons can be knocked off or gained easily, and the number of protons determine how many electrons will be held by the element at its neutrally charged state, and hence how many more it needs for a complete outer shell. Neutral charge is an element's most commonly occurring state. Adding to this, it is extremely difficult to separate a proton from a nucleus and needs huge amounts of energy, so overall, the proton number most uniquely determines an element and its chemical behavior. An isotope is a variation of an element where different variants have different numbers of neutrons but the same protons. Different isotopes react the same chemically, but have different physical properties, since they have different weighted atoms, so may be more or less dense than one another. Chemical behavior doesn't change because the charge on the nucleus is the same amongst all isotopes of the same element. Separating or adding a neutron or a proton is extremely difficult, which is why isotopes are so rare to find and nuclear energy is so dangerous. Another important note: a mole of an element is 6 times 10 to the power of 23 atoms, regardless of the element or its molar mass. 1 mole of carbon is 6 times 10 to the power of 23 carbon atoms. 1 mole of magnesium oxide is 6 times 10 to the power of 23 magnesium oxide atoms. 1 mole of plutonium is 6 times 10 to the power of 23 plutonium atoms. A mole is a fixed number and counts the number of atoms and not anything to do with mass. It is an important note. Let's say in a chemical reaction, 1 mole of potassium reacts with 1 mole of chlorine to form 1 mole of potassium chloride. You only have 1 mole of potassium chloride even though 2 moles of substances make it. When atoms join to form a bigger molecule, you still have 1 molecule, even if it is a larger molecule. When atoms form a larger molecule, the atoms act as a single cohesive unit. Moles are often used to quantify amounts since it is often easier to calculate them directly from a chemical reaction. As you know, different elements have different numbers of protons and neutrons. So an individual molecule of each element or compound will have its own mass. Relative atomic mass is literally the mass per atom of an element of compound, but scaled up to the mass per mole instead. The mass of an individual atom isn't useful, so we have the relative atomic mass as the exact same thing but scaled up. Let's also look at chemical equations in a new light. The key thing with the equations is that they don't depict fixed amounts, but instead proportions in relation to other reactants or products. They display the molar proportions. They don't display masses. They don't display masses. They don't display masses, for heaven's sake. The easiest way to go about it is to assume anything which has a 1 next to it means the amount is 1 mole, and then anything else has a number in front of it times 1 mole. Be extremely careful of which units are asked for, whether moles or mass are asked for. If you have a compound, you can work out its molar mass by adding up each part individually. E.g. in the example we just did, 1 molecule of calcium carbonate is made of 1 mole carbon, 1 mole calcium and 3 moles oxygen. We can then individually apply molar masses and add up the converted masses. Since it is just converting, it doesn't change the amount. Just converting from moles to mass. Since protons and neutrons have near enough the same mass, and hydrogen is simply just a proton, you can work out the molar mass of an element by simply taking the mass number and taking that to be the number of grams per mole, or possibly kilograms per kilomole. E.g. carbon has a molar mass of 12 grams per mole, and has a mass number of 12. The number of a mole may have been chosen as 6 times 10 to the power of 23, because that is how many atoms of hydrogen amount to 1 gram. Remembering that a proton and neutron weigh the same, you can think of it in this case as an element being made of loads of hydrogens as far as mass is concerned. E.g. 1 mole of carbon is made of 12 moles of hydrogen. The point behind this is that if there is 1 gram in 1 mole of hydrogen, then you can find the molar mass by taking the mass number of the element, since it's made of that many hydrogens, so the rule applies for everything. Allow me to show you a visual way of not getting your units mixed up. Let's try an example of converting moles to mass. Let's say we had the following reaction, but we knew we had 98 tons of calcium oxide. How do we work out the mass of calcium carbonate? Let me show you a shortcut method. The first thing to do is pick out an element which is in only one product and one reactant, so we know it must be the same amount of that element in each substance. We'll pick calcium. Using the molar masses, we can work out how much of the 98 tons is calcium. We know that this is the same amount of mass that is calcium in the calcium carbonate. The answer is 70 tons. Now let's work out by percentage how much of calcium carbonate is calcium. This amounts to 40% by mass, which we know is 70 tons. We can just use algebra to rearrange and find the original mass. But what about when it's more tricky? No problem. In this case we are literally going to do the same thing, except using elements that are in more than one place. We want to know the mass of hydrogen chloride. Hydrogen chloride has 1 mole of hydrogen, whereas water has 2, but let's find the percentage by mass that 1 mole of hydrogen would occupy in a water molecule instead of 2. We know how much mass 1 mole of hydrogen takes up in a water molecule. And looking at the equation, the same mass is how much 1 hydrogen takes up in a hydrogen chloride molecule. Now by finding the percentage, we can use algebra to work out the original mass, because we know both amounts are equal. Alternatively, since there is twice as much hydrogen in water than the hydrogen chloride, since in the equation there are 2 hydrogens in the water and 1 in the hydrogen chloride, we could just work out the total amount of hydrogen in the water and have it to find the hydrogen chloride. I'm sure that by this point you're wondering how a catalyst works. It works by providing what is known as a convenient surface. The result of this is that the molecules are more likely to bump into each other when confined to the surface, so they need less energy to move around enough to collide with each other at a fast enough rate of reaction. This means the catalyst lowers the activation energy, thus speeding up the reaction. It makes sense why energy is needed to break bonds, but why is energy released from forming them? Because normally atoms' outer shells and electrons will repel each other, which is a force, which takes energy. But when they bond, they no longer need that energy, so discard it. When energy or heat is supplied to them, they regain the energy and repel each other again, thus breaking off. Exothermic reactions happen when the energy released by forming new bonds is more than that of the energy needed to break the old ones, and vice versa for endothermic. You're probably also wondering what makes a substance acidic or alkaline. pH actually stands for potential hydrogen or power of hydrogen, which is how concentrated the substance is with hydrogen ions. Acidic substances have loads of hydrogen ions, so donate them to their surroundings which have less, whereas alkaline have very few, so take them. When an acid or alkali is not chemically reacting, they burn shit around them by giving or taking the ions, which happens by diffusion as the surroundings have more or less hydrogen ions respectively. You should notice how pH is ultimately concentration. A neutral or base substance is water, the most acidic is hydrochloric acid, and the most alkaline is sodium hydroxide. These 3 are actual compounds, and not mixtures like fruit, or soap or stuff like that. Let's take a lemon for example. It contains citric acid, but its pH is 2 instead of 1. This is because the citric acid is mixed around with water and stuff from the fruit, which weakens the concentration, so it's safe to eat. Hydrochloric acid and sodium hydroxide are pure compounds, and hence the most concentrated or least concentrated with hydrogen ions. On this note, substances like hydrochloric acid and sodium hydroxide are ionic, so the hydrogen ions can easily be separated with heat or when dissolved, whereas a substance like water covalently bonds the hydrogens, so doesn't give away its hydrogen ions. Although electrolysis seems complicated, it is essentially just giving back electrons to elements which lost them, or taking them from elements that gained them, and therefore reneutralizing the charge. Clean and simple.